For those of you guys that didn't do homework and are just now checking it at whatever time this is during the break, here you go. Here's 10. Here's 12. Here's 14. Pause it if you want to see it longer. Here's 22. Here's 28. Pause it if you want to see it longer. 40. How'd you guys do it?
40?
Yeah, sweet, right? Radians, right?
Yeah.
If you were in degrees.
It was choppy.
It was choppy. The graph was choppy?
Well, in degrees.
Oh, yeah. You have to go zoom trig, and then it's nice. Zoom trig is okay, but otherwise. Number 48, what were you allowed to do? Calculator. Now, my crazies. Whoever gave you sugar or coffee today should be something. Secant. Guys, real quick, you know how to put this in your calculator, right?
Yes.
You would have to do, you could do like 1/3 1 divided by 3 times 1 over cosine, but either way, you'd have to put all this bleh in cosine, right? And do 1 over. And then you get your little bouncy, fun. Okay, so.
Oh my gosh.
Winnie the Pooh and dinner
I
too.
got hit by it.
56.
Oh,
Wait a minute. What's going on?
yeah.
Here.
Hold up.
Hold up.
Hold up.
You're just you're going
Oh, yeah.
He's just excited. He's doing some partying this week. Okay, so. Come back. What were you supposed to do in 56?
We were supposed to find, I think it was the X's and then graph.
Okay. Why are they so specific? Why aren't they like decimals from the calculator?
Yeah.
Come on, you guys did unit circle.
Why are they?
Why aren't they decimals? They didn't use their calculator. They used what instead?
The
Unit circle. But who knows cosecant off the top of their head?
no one.
So, who is this?
It's actually the square root. Oh.
Hey, does that happen in the unit circle? Is the
Yeah.
y ever square root of 3 over 2 negative?
Yeah.
In what two quadrants?
In the third.
You guys love to play off. And then, yeah.
That's what I was gonna say. You just did it fast.
Wait, you did say third. I heard third. I didn't hear fourth. But remember, sine is the y is negative in third or fourth, or all are positive, sine is positive, so you can use negative there. What angle is this? This one, right? What angle is this? This one, right? How do they figure out those ones? Oh. And then, I think they went positive 2 pi, negative 2 pi. I think they might have given like a sort of range or something to say you can go between here to here. They're telling like where to start, where to end. Because otherwise, couldn't you go forever? We don't want to go forever. And then what was the graph supposed to be? Just a normal cosecant. So you do a normal cosecant off sine. Do a normal sine curve, up 1, down, down, -1. I can draw a sine. And then you bounce with your vertical asymptotes at the zeros, right? And then, who's this? It's a line. And where does the line hit? At 4 pi over 3, 5 pi over 3, negative pi over 3, negative 2 pi over 3. But the way to make sure that's true, you would use your intersect feature. You'd have to compare those decimals to what these actually are. I don't like the decimals. They're messy. So if we can keep it perfect with the unit circle, we do. We do. 58. This was from an earlier section, right, guys? That tangent is an odd function. Since he's odd, we could say he has origin symmetry. That's kind of an oldie but a goodie from chapter 1, chapter 2. Origin symmetry. But can you guys see it in the graph? What's on one side? Where does it copy? That's origin symmetry, right? It's not even. Even would be flipped over. It'd be like this. It's not even. It's not x-axis. It's not flipped down. It's origin. Okay. 70. I think this was the one I said put both of these in your graphing calculator and then mention the relationship. Guess what? You put both of them in. How many graphs do you get? Just one. What does that mean? They are the same. Oh, is equal to G. Done.
76. How would we possibly graph that? Like sketch it?
You wouldn't have to do it by hand. You wouldn't have to do it by hand. Because remember yesterday, these are the dampening ones. And the dampening ones, you have to know what he looks like. Because he is this top one, and he's this bottom one. And then you just know sign starts in the middle, and you say, hey, go hit, oh, go hit, oh, go hit. And then go hit, go hit. Right? That's the rough idea. But you would need to know what that looks like, and you guys haven't had to have that memorized, right? That's crazy. It's like an exponential, but with something way more complicated than an x. But what they were asking you to do was to graph it, and then try to fill in, what does the arrow mean again?
2.
No.
Approaches.
Approaches, right? So as x approaches infinity, do you guys remember how we're looking at the graph? If we're saying as x approaches infinity, which way are we going? Up, down, right, or left?
Right.
Good. And they're asking, what is he doing as he goes to the right?
Approaches 0.
He goes right? We could think it goes to a height of 0. And then what's going on for this little guy as, they asked a different question. As x goes to 0, okay, well, as x goes to 0, I guess it can go to 0 two directions, right? But where is the y going? All right. This is actually an important formula for calculus. But they were just having you use what you know about the arrow meaning approaches and being able to use some graphs of some kind of crazy dampened trig functions. I try to say that word very carefully. Do we have any more? Oh, we do. 84. You had to, I think it was a word problem, wasn't it? Or no?
Yes, the last those 2 words.
These two. Okay. 84 was a word problem that gave you a scenario. Basically, you had to figure out your triangle. And guys, if they're using cosine, what must you have been given and what were you finding? Which sides are these? Adjacent and bingo. So they use cosine, they did adjacent and hypotenuse. Okay, solve for, this is a little weird, solve for D according to the directions. I think it was distance, right? Yeah. They solve for the distance. And they got a function and they plugged that in their calculator. And they had their window be only between negative pi over 2 and pi over 2. I think all of that was, it was stated. Question. Can we, in our calculator, make the calculator only graph this over here to here? What do we use to have the calculator only graph a piece? We use the inequalities.
Or we can use N. Isn't it?
Yeah, the and the or stuff, the booleans. Do you guys remember how to put that in your calculator? You put in your function, which would be 27 over cosine. What do you have to put before you divide? So you do your function, a division sign. Do you remember the menu where all the stuff was? Second. It's in the test menu. Okay. Second math, there we go. Second math gets you, I think the inequalities go over to logic and it's all the words, right? You'd have to say x is greater than this one and, that's the logic one, x less than pi over 2. So your graphing calculator can just graph a piece, but Sean, what did you say when I was like, hey, can your graphing calculator restrict this to only two portions? You just make your window settings, hold on. Wouldn't this be x min?
Yeah.
And couldn't you make him x max? And of course, what mode are we in if we're talking about radians? All right. Last but not least, I really like number 90. He's probably my favorite. Maybe not out of the whole homework. Why? There's more arrows, and arrows are calculusy. Okay, what does tangent look like? He's a squiggle. Okay, that's good. Where are his vertical asymptotes?
Pi over 2, negative pi over 2.
So a little bit this way, and a little bit this way. And where's his 0? Is he going up or is he going down? Okay, so question. Just want to make sure that we remember the approaching stuff. Which direction are you coming from if it's pi over 2 with a little plus? Do you remember? A little plus. below pi over 2 or from above pi over 2? Above, because it's a little bit higher. Uh-oh. Maybe I should keep graphing my tangent. Remember there are lots of cycles? Maybe I should keep graphing my tangent. Remember there are cycles. Okay, hold on. So as we come from above pi over 2, so on this side, oh, go hit somebody, there he is. What happens is you come in towards it. Where's my function headed? Good, does that make sense? As I come from above, function's going down. As I come from below, function's going As I come from above this one, good, going down. And as I come from below this one, just a quick reminder of what the little arrows mean and how we think about, especially when we see the little numbers with a positive exponent and a negative exponent. All right, cool kids, closing this down. Those of you that did not have that ready for today, whoo, you're working on them over break. If you don't work on them soon, what are you going to probably have to do to even be able to tackle it? With some understanding and not just with cheating with CalChat? Watch the video all over again and then waste more time. Okay, so we're going to do it early. We're going to get it done-ish. Let's go at least introduce section 4.7 to show you what else maybe you should work on over break. Here we go, 4.7. Donde está? There it is. All right, I'm coming back here. 4.6 was supposed to be due today. Corrections are definitely due by the end of today to have full credit. We are starting 4.7. Homework 29, section 4.7 is going to be due the Tuesday we get back, but if you pay close attention today, Luca, listen. The corrections are due today by the end of the day. If you come in during lunch or after school, where are you turning them in? Yeah, the tray in the back in the folder, right? Or you could, I guess, put them in my box, but I'd rather them in here in the tray in the folder. This homework is due one day after we get back. We're going to work on section 4.7 a little bit more on the Monday we get back. However, what I was saying was, if you pay careful attention, 2 parts in the homework sheet?
Yeah.
Then both parts are due the Tuesday we get back. I don't want to make anything specifically to remember. So if you pay careful attention today, you're going to see possibly the way that you need to, or at least something you need to stay on top of over spring break, Thanksgiving break. Whoa.
Man, that's a
A
nice
student a couple days ago said spring break, and I keep on having to reorient what comes out as far as
Misty, when we come back, we're gonna have a test on Thursday, and then we're gonna have Friday and a week before finals. Is this week gonna be all of you, or are you gonna do like have a chapter?
Okay, so inverse sine. Inverse sine. Our semester has one less week than last year, so we're already kind of hurting. Ooh, so I don't want to make it any worse. Inverse sine. Okay, hold on. Before we think about inverse sine, wait a minute. Inverse. You guys remember, given the graph of a function, how we graph this inverse function? Not reciprocal.
Origin.
Not origin. They reflect over something. Where they reflect over? On the x-axis. It's a line. Which line?
Oh, the y equals x.
There we go. Okay, right? So like if you have x squared, who's x squared's inverse? What undoes a square? A square root. Remember what the square root function looks like?
Yeah.
If you put those two together, there we go. Are they flipping across the x-axis? No. The y-axis? Nope. The y equals x line. Yes. That's that symmetry. It's across the y equals x line. So, couldn't we get the inverse sine by graphing a normal sine?
Rhetorical questions, Sean.
Please go and explore. Okay, so you get the normal sine. You get the normal sine. And then we say, you know what, there's this line, right? The y equals x line. We graph him. He kind of cuts through the curve a little bit. No idea why he spazzed out right there. Okay. And then we say flip. Now, ooh, is this an easy one to flip?
No.
No. So what happens when it's not easy to flip? We flip piece by piece. What? Like, couldn't the one that's above now be below? Right? Piece by piece. Take it easy. The one that's above is going to be below. The one that's below is going to be above. Just play that one above.
She said not today.
Then, doesn't it go and meet the axis? What am I copying now? This piece. Go hit the axis. All right, go hit the axis. Concave. Go hit the axis.
Oh, so it's gonna be.
This one, doesn't he come hit the axis too? Wait a minute. Hey! Do you see the sine curve? I kind of do. He's just what?
It's over the y.
Yeah, he's going around the y-axis instead of going around the x-axis.
The asymptotes are 1 and -1, too.
Well, hold on. Remember, sine doesn't have any asymptotes. But cosecant inverse would. We can keep on going, but we'll just go ahead and stop and say, okay, we got two of them, right?
No, but this.
Okay, that's kind of fun. Kind of cool. I want you guys to go ahead and give me. Oh. So wait. If this is inverse sine. This is an inverse sine relation. Why am I saying relation and not function? What's it failing? Yeah, the original fails the horizontal line test, which indicates the inverse is going to fail the vertical line test. Now, I want you guys to go ahead and try to graph that same thing without a sign for the next graph. So what does just the inverse one look like? So try to graph it without the sign graph. This gets a little messy and we start to get confused as to who's who. You guys graphing them? Which direction do you go first from 0, 0? To the
Right up.
to the right, and then you come back, then to the and then you come back, right? Yeah, kind of. Then you're going to go to the left and to the right. Ish. That's a little too stretched. Now, here's the problem. Kiddos, can you read the title of the section real quick?
Inverse trig function.
But this isn't a function, is he? Okay. So look at the note at the top that you already wrote. Sometimes we need to restrict functions. We need to restrict functions in order to make them pass as a function. Or another way of saying it, sometimes we need to restrict an original function so that his inverse will be a function as well. We see that the inverse fails because the original fails, the horizontal line test. So if we're going to restrict it, here's how we're going to restrict it. We're going to say we need to go all the way over to positive 1 because sine goes up to positive 1. We need to go all the way back to negative 1. And we need to get all the points that pass through all of the values, negative 1 to 1, because those are all the different possible values that sine can equal. But we don't want any repeats. We don't want any repeats. So we're cutting our graph. We're cutting our graph to go all the way as far to the right as possible, which is 1, as far to the left, which is as possible, which is negative 1. As far up as we can go before it starts to fail by doubling back and failing the vertical line test. And as far down as it can go without doubling back, it would fail the vertical line test again. Now, hold on, calculators, do you have them close?
Mm-hmm.
Is there sine inverse? Is there a function for sine inverse in your calculator?
Yes.
What is it?
Sine.
Second sine. Is it the same thing as cosecant?
No.
Don't get them confused. It's sine, don't tell me -1, it's sine inverse. Remember the -1 can mean inverse? Go to your y equals, make sure you're in radian mode. Graph sine inverse and see if he looks like, not the whole slithering snake, but just the little piece that we got. He is restricted because what mode are you in? Function mode. What's the only thing that you can graph in your y equals? Functions. So why isn't it graphing the other one? Because we can only graph the function part, which is just from what angle? Wait, angle, huh? Doesn't sine have angles here and ratios or values there? What's going to happen when I switch everything for the inverse? What's the x now? In a sense, the y. But I'm going to go ahead and put the ratios, and I'm going to put the theta right here. And just to make this match, we'll say the ratios. What ratios? All the opposites over hypotenuses. The 1/2 and the square root of 2/2 and the square root of 3/2 and the 1 and the -1/2 and negative root 2/2 and negative root 3/2 and -1 and everything in between. The ratios are the x's, the angles are the y's, which is why I asked what y value or what angle would match with sine being 1. And if it helps, you can think about this one. What angle happens for sine normally right here at the maximum? Not pi, close. Pi/2, why? How long does it take for sine to complete, guys? What's its period normally? 2 pi. So if that's 2 pi, then who's that? 1 pi. 1 pi, and who's that? Half pi, and that's 3/2 pi, right? So then we can say, how high does this little inverse guy go? Pi/2. And guess, because of the symmetry, how low will he go? -pi/2. And that gets us to our domains and ranges for inverse sine. Look at the blue only for inverse sine. I'm going to go ahead and write inverse sine's equation. You guys already got them in your grapher. Y equals sine inverse. Right? Not cosecant. They're not the same thing. But sine inverse is going to go how far right, how far left? Uh-oh, they kind of coincided. How far right, how far left? Well, remember we always start with the left one, -1, to the right one, 1. That's the domain. Range, how low, how high? Well, how low will he go? No, remember we have to cut it. 1 and -1 is how right, how left. How low, -pi/2, to how high, pi/2. Real quick, can we just use our unit circle knowledge to put a little unit circle over here and show exactly what those angles are? How do you go -pi/2? Go down, and down how much? Down 90, right? And how do you go to +pi/2? Go up 90. So inverse sine is only looking at angles between -90 and 90, aka only angles in quadrant 1 and quadrant 4. In quadrant 1 and quadrant 4. Okay, a couple more seconds. I know, this one, we're introducing all sorts of stuff. We'll go ahead and try to work out some things in the next page. So the next page, you guys already have it down, right? Inverse sine functions. Inverse sine functions. Y equals sine inverse of x, or another snazzy way of showing inverse trig is to say arc sine. It depends on what book you're using or what problems you're using, who wrote them as to what they might write. So real quick, sine inverse and arc sine mean the same thing. They mean the same thing. But that is only true if and only if sine of y equals x. So if we flip the x and the y, we're back at a normal sign. Not a reciprocal, remember sine inverse does not equal 1 over sine. Does not equal cosecant. So let me go ahead and show you what's going on with this, okay? So if we were to take a normal sine fact, okay, someone give me an angle in radians, any angle, I don't care. Pi over 3. What does sine of pi over 3 equal? 60 degrees, you go up a lot.
1,
Who is that?
2, 3, square root of 3 over 2.
Yeah, square root of 3 over 2. If this is a statement we're used to making, what changes when we're dealing with inverses instead? Well, in this one, it took me way too long to write it, sorry, hold on. It's making me move it piece by piece. In this one, we said sine of an angle equals a ratio. For inverse, we're going to say sine inverse of the ratio should get us back to what angle? Do you see the difference? Sine says, hey, give me an angle, I'll give you the ratio. Which is why in a unicicle quiz, every single one of those problems said, hey, sine of, give me an angle, cosine of, give me an angle, tangent, give me an angle, and you guys, after I gave you an angle, you would give me the ratio. 1/2 square root of 3 over 2, square root of 2 over 2. If you were solving with right triangles, I would give you all the info, and you would give me the opposite over adjacent for tangent. The opposite over hypotenuse for sine. So you're used to getting angles and giving ratios. Sine inverse says, I'm giving you a ratio and you have to go backwards to the angle. You have to go backwards to what angle it goes with. So, hold on. As we look down here, different examples. Now, first of all, arc sine, sine inverse, same thing, right? These are all the same function. This one gives me negative 1/2. Is that an angle or a ratio? Angles go in who? Sine. Ratios go in inverse. So these aren't angles, these are ratios, okay? And if you're thinking about ratios, remember, in our unit circle, when we're talking about x's and y's, it just helps, right? We have an x and we have a y. Sine of, this is our theta, and this is our y value. This one says, give me the y value, I'll tell you the theta. That might help a little bit too. Remember the unit circle? Sine is equal to y for some sort of theta. Sine says, give me a theta, I'll give you the y. Sine inverse says, give me the y, I'll give you the theta. So then, does that help a little bit?
Yeah.
This is the y. Or if you want to think about it, this is the opposite over hypotenuse for SOHCAHTOA. Either way, it's the ratio. So if you're looking at your unit circle, why don't you guys go back there really quickly to section, what was it, 4.2? Where your patty paper is, it should kind of stick out in here. Okay, question. There are two different angles where sine, the y value, is negative 1/2. Can you find them for me? What angles have the y value be negative 1/2? 4 pi over 3, and what else? I agree with the 11 pi over 6. I think the 4 pi over 3 is wrong.
7 pi.
There we go. Because these should kind of be symmetric, right? Yeah. All right. Question. Didn't we just write down for sine inverse where we're supposed to legally be looking? What quadrants? 1 and 4. We're only allowed to be looking at answers that go up 90 or down 90. Question. Does this up 90, down 90 go through either of those answers? Yeah. Which one? Okay. Why am I not going to write 11 pi over 6 and instead I'm going to write as my final answer negative pi over 6? I'm not allowed to go around the big way or the long way because what was that range. We're only allowed to go negative 90 or positive 90. Negative pi over 2 to positive pi over 2. So we're not allowed to go around to the 11 pi over 6. We're only allowed to go down pi over 6. Or you can think down 30.
Why?
Because remember we had to cut this and only use negative pi over 2 to pi over 2. So we're only allowed to go down 90 or up 90. So I can't go up 330, that's illegal. Okay? Now, hold on. So are we saying the only time sine can equal negative 1/2 is right here when you're rotating down 30 degrees? No. But we are answering the one, what we're going to call the principal value for the inverse sine function. We're using one representative answer. But if there are infinitely many different answers, is that very helpful when we come to like a test or when we come to like, I don't know, the mathematical community talking about a certain sine inverse? Is it helpful if everyone can have infinitely many different answers that are all right? No, we want a standard. And the standard is negative pi over 6. So if you plug into your calculator real quick, not in the graph, in the home screen, go second sine of negative 1/2. Go second sine of negative 1/2. Is your calculator going to give you infinitely many answers? No, it can't. It needs to give you one answer. Why don't you go ahead and after typing that in, you get a decimal. Can you write in negative pi over 6 and see if it's the same decimal? The answer is yes. We're getting the main answer, the beginning, the standard answer that the calculator would find, that any back of the book or math problem would find, etc. We call this the principal answer. Now, kiddos, help me out. Can we go to another one? In your unit circle, question. Are there any places where y equals square root of 3 over 2? Yes, where? Y is up a lot at pi over 3, and he's up a lot at?
5 pi.
Ooh, careful, he's down for those ones. So he's up for pi over 3, and he's up for 2 pi over 3. Question, do either of them work in our restricted range? Yeah, but which one? Pi over 3. Does that work in my negative pi over 2 to pi over 2? Yeah, he's not too big. He's fine.
Missy, why did you give that one negative pi over 6 and not 11 pi over 6?
Because remember, it's only allowed to go from negative pi over 2 to pi over 2.
Oh,
11 pi over 6 is
you don't
way
consider
too big.
this or this?
Right.
Okay.
Up, down, down. Now question, kiddos, hold on, before we finish, because I know it's about to be done. Do you see that inverse trig goes backwards? Uh-oh, stink. If inverse trig goes backwards, then we need to know our unit circle even better than we do it before. Right? Okay, so some of you need to catch up on getting with us in the sense of having all the homework 1 through 4, 6 done and having it all graded, right? Okay, others of you are like, and caught up. All of us need to work on that unit circle. And so as a result, if you, all of you have some sort of electronic device, right? If you email me at any point during break before the Monday we get back some sort of at least 30-second video of you being quizzed and answering unit circle problems, I will give you that. Hold on, what are the stipulations? Email to me. Oh, you're gonna have someone like showing me answers. You can get stuff wrong. I'm not saying get it all right, but hopefully you get most of it right. What are you supposed to do? Email, right, before the end of break, so before Monday, so we'll say by midnight on Sunday night. How long does that have to be at least?
30 seconds.
30 seconds, and you have to be doing what? Someone, you put questions or something, is quizzing you on the unit circle and you're answering as best you can.
Okay.
You have to get it down like this. You gotta be speedy. Bye guys.
Okay.
Speedy in college. Yeah.
How do you want it? What principle? What's a good example?
Like sign a fire with 3. Like, oh, sorry. Yeah.
Are we allowed to draw the unit circle like you can
You're allowed allowed to, well, in the 30 seconds, you can't have like the answer go in front of you, but you could theoretically, part of the 30 seconds are you like drawing it and then using it to answer questions.
Yeah.
But it has to be less than 30 seconds and answer.
So if
So you could start with blank paper.
Yeah.
You could have the person who's videoing like be on you and be like, go.
yeah.
And then you draw it and then you're like, okay, go. You have to answer at least a couple before.
So like how many? What's like your requirements on camera? Like 5?
I just said 30 seconds, so you need to get your, whatever your cheat thing is that you like, you need to get drawn and answer, let's say at least 2 questions.
Okay.
But you can go longer than 30, I just said at least 30.
Oh, okay.
So
Okay.
I just need to hear you correctly using however you're doing it and as fast as you can.
Oh wait, and then I have another question. Yeah. Okay, so for tutoring and stuff like that, if we want to go to like Starbucks and meet somebody